Okay, sorry, I interrupted the video accidentally, but it's good. We have a pause. It was long anyway. So I was just briefly introducing the difference between different kind of product. In algebra, this product is 2 times 3, for example. 2 times 3 is 6, and we have a dot or nothing, and it still gives a number. And then this called just I don't know, scalar product. I don't know. And then when we have vector x and y, we can do a product between x and y with the same dot. And then this is a bit more complicated, but we saw worse than that, because I will show you in a sec. But x1, x2, let's do dimension 2 times v1, v2, and this is the dot. In this case, it goes like x1, v1 plus x2, v2. And as you can see, the dot turns vectors into number. This is a number. If we may put coordinate like 2, 3 times 1, 3. Hope I don't make mistake. It's 1 times 1, 2 plus 3 times 3, which is 2 times 9. It's 11. Okay, so this is 11 in this case, and this is called scalar, because a scalar is a number, and then whatever, and this is two vectors, and this dot product, scalar product, turns vectors into numbers, vectors into scalars. But we saw worse than that. We saw a product that do not go into numbers. For example, we have this product here, 1, 1, 1, 1, with a matrix times the vector 1. If you remember, the product is 1, 1. And this is a product between matrix and vectors. I don't remember the name, but matrix dot, it's another dot product, and it doesn't give a scalar. This is a vector, and it's still a dot. But the angular momentum is a different kind of product, and because it gives a vector, it takes vector into vectors. Okay, I don't know if there are any others that do the same services. Maybe there are. I'm sure there are. I mean, you can invent whatever you want, so sure there are. But let's do x times v, and this is, how was it? Oh, I forgot. Sorry. X times v, it's a vector, so we do x1, x2, v1 vector, v1, v2. Now this is a bit annoying. We need to do like a determinant into dimension. So x1 v2 minus x2 v1. Okay, so in the direction of oh yes, I forgot. So if this is x, let's do it correctly, otherwise I get confused. x1 over y1, x2 y2, and this is the determinant x, y, x2 y1. Okay, I have in the z direction. Okay, so it's weird. I mean, it can be done in other ways, but I don't want to go that in depth. But just to give an impression of what it is, it's a number. This is a number that is made out of these 4 numbers here. Okay, and then these numbers are usually in the same plane, x and y. If you remember, there is the distance and the velocity. They're in the same plane where the rotation happens, and then you and then you stick out the vector z in this case, which is orthogonal to those two vectors, 90 degree, as we said. Okay, now this is one case where and this is the simple case where okay, this is the generic expression. Okay, there are subtleties here. I don't want to go into the detail now because it's a long it's annoying math, but basically if the vector v, d and v are not 90 degree, this angle is alpha, you can still define the vector product with modulus v modulus d, so the length of the vectors times sin alpha, and the direction is still z. So I mean, it's the important thing is that it's not a scalar, it's a product that creates a vector, and the vector is orthogonal to the one that you put here. Okay, so angular momentum, if you do the scalar product of the vector L times x will be 0, and the dot product of L times V will be 0. So they are orthogonal. Okay. Okay. And the last thing that I want to say is that technically speaking, and this will deserve another video, which I'm not going to do right now, because I want to talk about a little bit about the electron, and see if I can load the video at the end. Okay, the only thing I want to say is that it's not technically a vector. It's called pseudo vector. And this because, and I will not give you all the detail. I will link to a Wikipedia page which is, I think, very clear on this. I don't want to make a mess now. But basically, it does not behave well under rotation, reflection, and translation. Meaning that when we apply a rotation, so when we rotate the object, we move the object, or we reflect the object, like in a mirror, when we have the mirror. Okay, this vector here doesn't transform, doesn't move as velocity and direction, or acceleration, or other physical quantities. It picks up a minus sign, which is necessary for the physics to be there, but it's a mathematical sign, and you can see easily in the definition that I showed you before that there was a minus, right, between the components x1 y1 minus x2 y2. If you just interchange x and y, you flip a minus, right? If you change 1 and 2, the position of the coordinate with the rotation, there is a minus the new one, because this minus x2 prime x1 y prime, sorry, there is this minus here that is changing when you rotate the component. Okay, so it's a pseudo vector, but we don't care about this because for what I will need to show you later on is just that we will not even care about these marks, but it's just to remind you that angular momentum is not technical vector. Pseudo vector is not a piece of math. It's very important in physics. It's in the way in all the calculations. So I mean, sorry for whoever is into the field. They know what I'm talking about. For those who are not familiar with these things, it's just I think an interesting thing to know that not everything behaves well. Not even in math in nature, so we need to constantly adapt to what happens, which is fine. Okay, so how I'm doing? Okay, so what I will do, I will definitely do other videos on these things. I'm not prepared to do the math on the hydrogen atom, which is heavy, but I want to give you an idea of what the result would look like. So we said, and this is the final bit, hydrogen atom. Okay, we said that the idea of the electron orbiting around the proton like a planet around the nucleus, it is not this is a atomic model. I don't remember who came up with this. A long history of people who worked on that. Before there was a different model where the electron were inside the nucleus, like in a panettone, raisins in panettone. But that would Rutherford, I think, made experiments to show that that is not the case. So this was called Plum, I think, model. I will put some references, but that model is gone. Then there was this atomic model one where the planetary, let's say planetary, and even this one was disregard because when and this is the tricky part in special relativity that I don't want to touch, but I will just give you the result as far as I remember. One electron is moving in a circle or in an accelerated environment, it emits energy. This is a fact. We know that. Wait a second, I lost my pen. Yeah, it emits light. So since if electron was rotating, this is what you see anyway in, I think, in aurora borealis, somehow charged particle in the magnetic field. They have a curved trajectory and they emit light. But anyway, they emit light, and if you emit light, you emit it from somewhere, you lose energy, meaning that the more you spin around the nucleus, the less energy you have, and at some point you collapse around the nucleus. And this is the same idea of having your stickman waving your rope, and then at some point you decide to reduce the speed at which you make it turn. If it's very fast, it will stay in orbit. If it reduces it, it will gradually slow down up until it will stop and collapse on your feet. Okay, so this is the same thing that should happen if you combine classical mechanics, plus special relativity. They don't go well with this atomic planetary model. And then what happens is that you need to, lots of physicists, maybe not lots of, but some very famous physicists came out with a different approach but from a different angle. They saw an experiment that didn't quite match the result expected from these kind of atoms, and then they decide to take the approach of studying, and I will just write it down, studying the atoms with this new theory, which was quantum mechanics, and this was one of the first. And we remember a little bit about quantum mechanics. We remember that H plus equal energy plus. This is the so this is the equation that I wanted to solve, where they are called stationary states. We said it already. Stationary states, meaning that the energy is fixed. There is no time evolution. Okay. Otherwise, there would be, you remember, the derivative of the psi. But if the derivative of time is constant, you get the energy. And this is the energy, and you have the usual suspect. You have 1 minus mv squared, the velocity, minus the kinetic, the potential, which is the potential is like so, E times divided by a constant by the distance. This is the potential, and this is the charge of the electron around the nucleus. This is the kinetic energy. This is the potential energy, and this is plus, and this is energy times psi, which is your state of the system, which is a complex vector. Okay, now I won't go. The last thing that I want to do is to recast this in a way that we know, with the operator that we know. So velocity mv is p, momentum, the operator p that we know. So we can write this like 1 p square m, and then this is alpha, a constant alpha divided by 1 over the operator x. And these are things that we know how to use. We saw, and we will try to solve this equation next time. But for the moment, I want to say 2 things. I would appreciate some question if you want in the chat. I can try to address them. A friend of mine asked me to answer a question that I will. So next video would be either hydrogen atom in depth, or why the light of a laser shines farther away than a torch, for example. This is a nice, interesting question that it's not easy to answer, so I will take some time. But as I said, if you have questions, if you spot mistakes, just let me know. And the other thing is that I will upload, hopefully, a video about this hydrogen atom, and I hope you will like. For today, it's enough, I think. Hope you enjoy. See you next time. Bye.